Hello guys, my name is Minhajul Islam from group 324. My topic is about the coupling of chemical reaction to transport of matter from the book M. Wolkenstein. The organisms and the cell or chemical machines that operate as a result of chemical reactions and transport of matter between the cell and the surrounding medium and also inside the cell. The transport occurs in a certain definition direction perpendicular to the circular and intracellular membranes. The flux of matter is a vector. At the same time, the rate of chemical reaction is a scalar. As has been pointed out, the direction coupling of scalar and vector processes is impossible in an isotropic system by virtue of the Curie principle, nor it is possible in an isotropic system having a center of symmetry. Biological system in which chemical reactions are coupled to diffusion, namely membranes, are however made up of chiral molecules which have neither a plane nor a center of symmetry. Biological membranes are anisotropic. In such systems, directing coupling is in principle possible. The vector coefficient may be different from zero. No theory of directing coupling between chemical reaction and diffusion in membrane has been worked out so far. One can visualize, for example, the transport of some reaction participants along the screw channels in the membrane in which the centers are located. Then the course of the reaction will be different from substances supplied from the opposite ends of the channel. The same result is obtained by considering a symmetrical channel in which asymmetrical reaction centers are regularly arranged. Therefore, is however no ground so far so stating that these effects are considered. The interplay between chemical reaction and the transport of matter can also take place by the indirect coupling which arises due to the steady state condition. In the stationary state, the irreversible processes that are not directly coupled become interlinked. Let us return to the example considered on page 330, along with the substance that participate in the reaction. These are the reactions. This provide an indirect coupling of the transport of substance through to the chemical reaction. We shall consider indirect coupling in the general form. We shall write the dissipation for function for a system in which a transport and a chemical reaction takes place. Above is the example, the reaction for that. We integrate for a one-dimensional flow along the x-axis from x is equal to 0 to x is equal to a. The total dissipation per unit surface is equal to this formula. The sums in the last terms of the right-hand sides of these expressions represent on the values of reaction affinities at the membrane bound areas x is equal to 0 and x is equal to a. Here are some other formulas regarding this. Then we divided the expression by a and then obtained microscopic phenomenal expression. Thus, the macroscopic coefficient is from above all these equations which characterize the indirect coupling of diffusion fluxes to a chemical reaction or expressed through microscopic coefficients. The Onsager reciprocity relation remain to be valid. That the microscopic coefficients of coupling are different from zero is determined in an isotropic system by a stationary state condition. As shall we see later, indirect coupling plays an important role in the theory of membrane transport, and we shall also discuss indirect coupling for so-called facilitated transport, which involves the molecules of the carriers.